kind of dug up, now what they weren't understanding was the risk. So if we go to the next slide, just to kind of highlight this risk and what we were trying to balance here. On the left, if we had a condition where we were in spec, but on the low side, if we, measured that out, well, what would happen? The business, we could not make as much money, we could lose money. On the right side there, if you're actually truly out of spec on the high side, that's a loose clamp. That's a loose airbag, won't inflate, not good, right? We have a end user, a customer could lose their life. So we really want to be in the middle here in the happy place where we have our process variation and our measurement variation happily within those spec limits. So that's a little bit deeper dive on the risk and the why of measurement systems analysis. And if we change gears, Jason, next slide, we'll talk about what is a measurement systems analysis. And at the heart of it, it's really a designed experiment, and it's designed to measure the limitations of that measurement system. So we want to find that truth, the actual value of the part, but we're clouded by this measurement error. So this experiment that we design is really designed to tease out that part-to-part variation, so the product variation, and then the measurement. So you measure that, and that's all intertwined together. So this design of this experiment is we want to tease those individual components out. Now, Jason, I've been familiar with the AIAG, the Automotive Industry Action Group, Gage R&R method. So I was curious, really, what's this EMP methodology all about?
Well, I think maybe a good way to answer that question was a story. It's a story about how I came to understand this evaluating the measurement process method, EMP, pioneered by Dr. Don Wheeler. I had myself and my team, my past job, had just completed a measurement systems analysis, and we did it on a fairly important gauge for the company. In fact, this gauge has been used in industry, or at least similar gauges have been used in industry that I worked in for some time. All right, fast forward a little bit. We get to the end of our study. We're following the American Industry Automotive Action Group standards, the percent R&R. And we see that we have a 40%, it might have even been a little higher than 40% R&R result.
Uh-oh.
Yeah, exactly. Uh-oh. Well, what does that mean? Well, that means that's unacceptable. Well, what does unacceptable mean? So we started talking about it. I reviewed it with our stakeholders and the team. And everybody's scratching their heads thinking, well, this isn't really telling me anything relevant, because this gauge has been making perfectly adequate business decisions for over a decade. So why are we saying that we want to condemn this gauge? And either, we would, if it really were true, we would consider either replacing it, come up with a new idea, or making an improvement, which would be extraordinarily expensive. So what happened is the question. And where does EMP help? And I love this graph. It comes from EMP3, Wheeler's book. And what we're showing here on the top is the percent R&R thresholds. So remember, 10%, 20%, 30%, right?
Yep, got it. I see that.
Yeah, anything over here is bad, unacceptable. Well, check that out. If I follow Wheeler's methodology, that would fall into a first-class monitor category. All three of those.
Wait a minute. Okay, that's new to me.
It was new to us too. And all of a sudden, hey, we need to learn more, because this is all of a sudden reflecting more of what our understanding and practice is, and as opposed to, just looking at these arbitrary thresholds. So I got a little simulation. Let's see if we can tease out what's happening here. Let me pop up a control chart really quick, and we'll tell you what we're looking at here. Okay, in this simulation, imagine that our gauge has been monitoring a process for a period of time. If I were to control chart the measurement process, or chart the measurement process over time, I mean, this looks fairly in control. Sure, we're throwing some control chart alarms, but that's kind of to be expected. Now imagine this. At some point in time, we have in this case, 1 sigma shift in the process.
Okay.
And we're still measuring it within this case. Let's just start out with a 30% R&R, like right on the threshold of unacceptable. Now take a look at the post-process shift control chart, Clark. What do you think?
Well, you say 30% Gage R&R, and I'm going, well, we shouldn't be using it. But what you're showing me here is leveraging these control charts. We can pick up that shift. And I think I had this aha moment of Wheeler saying it's a first class, second class monitor. So we're monitoring this process, so we can pick that up.
We can, and I love the nuanced language that Wheeler uses, because it is teaching us something. So let's monitor the process with an even less perfect gauge. Now, I mean, sure, we may not be picking up everything with a gauge with 40% R&R, for instance, but look, we're still picking up a lot of alarms, which would definitely, I mean, if we think about the odds of catching a 1 sigma shift with this gauge, we're looking pretty good.
Pretty good. Pretty good.
Yeah, and so this really is at the heart of what Wheeler's guiding us to in measurement systems analysis. The purpose of that measurement study is not to condemn the gauge. The purpose of the measurement study is to understand how to use it. So I feel like this kind of nails that point a little bit, Clark. I mean, what do you think?
No, this methodology turns the AIAG kind of on its head and comes at it from this whole usability utility perspective. So this is awesome. This is great.
Yeah, Wheeler has a lot of other things to say about the AIAG. He's got mathematics and stuff, but I think we'll leave it as this, because I think that tells the story fairly well. All right, we are going to be going into a case study, but before we do that, I think it's important, Clark, that maybe we tease out a couple of the important terms that we're going to be using in the EMP process. The first one, if you remember the graph that I showed earlier, hey, we have this intra-class correlation coefficient that's being used to classify our gauges. And again, there's some utility in the classifications, but I think we need to understand, what the statistic is telling us. It's really simple. It's the portion of variation attributed to the part. And that's with or without bias factors. So if I look at the denominator, this within, that's repeatability. If I look at these two, these are bias factors. So
okay.
Right, you're thinking.
I'm thinking that caliper measurement, this is where the, whoops, I could get this in spec here, but we get a penalty here.
Exactly. There's your operator bias in your airbag study. So in an ideal world, we would have a gauge that measures the same parts perfectly over and over again. So that term would be gone. We wouldn't have any operator influence on the measurement error. And
Right.
if we don't have any operator, we can't have any operator part interaction. So no interaction variance. So in a perfect world, our interclass correlation is going to be 1.
Okay, I got it. All
right, next one. And I like this one. I'm going to read this slide from bottom up. What we are talking about here is a way of determining how many decimal places to report. So what do you think about that? We're going to use stats to determine how many decimals to report, Clark.
So I haven't studied this whole thing yet, but just seeing this methodology, it's, we rat hole into discussions on resolution. Does the data look chunky? Well, that's too chunky. That's not chunky enough. And this methodology looks straightforward. That's something we could all agree on. And hey, this is what the resolution and measurement increments should be.
Yeah, I totally agree. I mean, it makes it a lot more objective, a little less to argue about around the team table. But really, it's based on this idea of probable error. I really like this quote from EMP3. No measurement should ever be interpreted as being more precise than plus or minus 1 probable error, since Measurements will err by this amount or more at least half of the time. So if you kind of wrap your brain around that a little bit, we're going to look at a range. We're going to bracket that probable error, and we're going to use that to help us decide on how many decimal places to report. There are other stats too, but I think, Clark, I think those are probably enough to get us going. What do you think?
I like it. I like it. Let's keep going.
Okay. So I understand you have a case study for us, Clark.
Yeah. So my wife is a avid cook, wannabe chef, and she likes keeping her knives sharp. And I actually just recently bought her some shun, some Japanese steel knives. And of course, the geek in me wanted to understand some of the variation, or maybe correlate hardness to how long the blade will stay sharp. So I called Shun USA and said, I want 4 knives from the same lot. So they we got you. So they sent me 4 knives, and I went and researched hardness testers, and I found this rebound hardness tester. And I know, Jason, you've used these before, but they're a handheld unit, and it kind of fires like a gun and rebounds, and that rebound measurement correlates to hardness. So the factors, of course, are just what we just discussed: the operator, so the chef in this case, the part, which is the knife, and of course we'll have our chef and knife interaction, and the scale or the measurement is going to be this Rockwell C hardness scale. So I've collected some data with 4 chefs, and curious about how this analysis or maybe setup might look in the EMP method.
Sure, and here's our data table, and maybe we could talk about the data table after we have a small discussion about designing the measurement study.
Absolutely.
So we had to get here, right? And you already introduced this idea that measurement systems analysis is a designed experiment. And that's kind of a clue for us. If we want JMP to help us design the measurement study, and we know it's a DOE, we're going to go to the DOE platform. And then there's a special purpose design utility for MSA design. But this is really cool. It works much like other DOE platforms like the Custom Designer. So we would just input here, hey, our response is hardness. That's the thing we're measuring. We have 2 factors in the study, so we'll add those. And the first factor is our operator.
Chef.
We can put chef. Yeah, I'll stay consistent with the table that you collected. But yeah, here's our chef. We can change the role, which will help JMP in the analysis component of this that we're just about to get to. So we're going to call that operator. The next one is going to be our part or knife. And this is the important one that JMP needs to know. And you said what? We have 4 operators and 4 knives, right?
You 4 chefs and 4 blades.
Okay. And we know we need some repeat measurements in there, right? We have to get that within variation, repeatability. So number of replicates. We're going to take the initial design, we're going to run it, and then we're going to run it again and run it again. So we're actually running 3 trials. So when we say replicates, we're taking the initial one and repeating it 2 times. All right. Talk about randomization a little bit here, because I feel like it's really important. And this, your example of, measurement squeezing, your operators squeezing and changing the way that they hold a caliper, it kind of comes to mind in terms of randomization. Clark, you want to give us your thoughts on randomization?
Yeah. Running these MSAs before, I've experienced, you can present operator with parts, and whether we realize it or not, we seek to reduce variation. And if you leave them alone, I've seen measure multiple parts, and then next thing you know, the operator has laid those out in the order they think that they can repeat it. So they're already biasing. So you really need a good proctor when you do these studies. You'll come in and get those parts out of the lab and then bring them back in and present them in a different order or one at a time. So complete randomization is key.
Yeah, and granted, I know that there are some circumstances where that's not possible, but the complete randomization is at the top of that pile for a purpose. So do your best is the guidance we're sharing. All right, when we make design, this is also, again, very similar to tools that you'll see in like the custom designer. We have some design diagnostics. We don't have enough time to go into these today, so we'll leave it up to the audience to explore this. But the way I might approach design diagnostics in the MSA design is asking questions like, do I have enough repeats in there to get the answer to the question that I want, for instance? So lots of tools packed in here. We're just going to assume we're happy with this, and we would make a table, and we'd go have our proctor print out a random run order, have our proctor hand parts to our 4 people in the Gage study. So maybe your neighbor can do this.
There you go.
Study.
Got it.
All right, let's head over to the analysis part of this now. So we've collected our data, we've done our rebound hardness, collected in a random order. Operators were blind to parts. Launched the measurement systems analysis platform. Response is obvious. Let's populate these. The way we've named the columns helps us know which role that they're in, but you could have them named anything. An operator, you can have more than operators a grouping variable, right? You could have different rebound hardness testers.
Rebound testers, maybe, okay.
Yeah, maybe your neighbor has 4 shun knives and wants to be involved in the study too. So you can have more than one grouping variable. These options over here, first one, EMP, that's default for a lot of the reasons that we've just shared in our story. But if you had to do a Gage R&R, traditional Gage R&R, you could turn that on. If you come from automotive, then I think there's an obligation to do that still. So I would encourage doing both, but that's how you would turn that on. Chart dispersion type, Wheeler has some guidelines on this in his book, and they have to do with the word Clark said earlier, whether our data are chunky or not, chunky data, non-chunky data. I have this set for standard deviation, but if our data were chunkier, we'd probably choose range. And it has to do with the control limit calculations. Okay, model type, we're going to say it's crossed. We already thought, hey, we've got some interactions involved here. I think that's all we need to get us started, Clark. And why don't we just go through the graphics? If you look at this average chart, what are your thoughts? What are your questions?
Yeah, I'm looking at this. I can how it's laid out with the operator, and we're looking at averages. I could start to see maybe a little bit of I guess operator to operator bias, like operator 1 versus say 3 is on average measuring lower. I was curious, there's some control limits on here, Jason, and this process looks out of control, but so I haven't really looked at this chart in this way. Yeah, could you help me understand that?
Yep, weird instances where out of control is good. So when we have all of our points falling outside of the control limits, it's an indication that the gauge is able to measure differences in our parts. So out of control in this case is exactly what we want.
So the spread, the total spread relative to that control limit, we want to see that. We want to see signals there. Okay, I get it. Now, interesting. Standard deviation chart, that's coming from the within, right? That's coming from the repeatability. So in my brain, that starts to say, I want this to be in control. It means my repeatability is good.
You nailed it. That's exactly
I got it.
What it's showing.
Okay, out of control average, in control on the standard deviation.
All right.
One other observation real quick on the average, the pattern or that sequence is sticking out to me. And I see in general a similar pattern, but I see deviations from that pattern. Say operator 1, part 1 doesn't kick up like a tail like the other operators. And maybe even that part 3, that and my brain starts to smell like an interaction. Something's going on between the operator and the part.
Totally agree. And maybe another way of looking at that would be a parallelism plot.
Ooh.
So we're just overlaying these on top of each other. And as the chart name suggests, we're hoping that all these operators are somewhat parallel. What we really don't want to see is lines from one operator crossing lines from another operator, because this is a visual indication of that interaction variance.
Okay, that makes sense. So if they were all parallel, no interaction, but now you see if there was a vertical displacement, that's where we're seeing on average differences, but the bias between the operators. So interesting. So right away, visually, I can see interaction, and I can already start thinking of a hypothesis, like what's different about that one knife or how it's being held.
Yeah, what I love about this is that, I mean, we're very minimally tipping our toes in the statistics. We're in the graph.
I love it. I love it. This is great.
All right. So one more. How about one more?
Okay.
What are you noticing here?
This is what I was trying to visually see in that average chart, but this is just reducing that to showing the average for all the measurements. So I can clearly see like operator 1 is biased low, 2, 3 are on the high side, and operator 4 is in the middle. So there might be some procedural, something's going on there that I want to go investigate and potentially consider for improvement.
Yeah, definitely. So all these graphs kind of help us. We're imagining what we're going to do next, either in using the measurement system or improving it. All right, so now we're back to the intra-class correlation. I'm just going to highlight 3 of these that are calculated in the table, and I want you to give me your thoughts on those.
Okay, looks like that first one, ICC no bias 0.98. That's awfully close to that one that we said, which is removing the operator and the interaction. So maybe that shows our potential of the system if we were to go try to get operator and the operator part interaction out. Then with bias up, and then with bias and interactions, and we drop off. So we're roughly 75% right now with bias and interaction. Yep. Okay.
The second class monitor. In fact, hey, here's a little control chart. In fact, my simulation is totally based on this monitor classification legend. So let's see what that means in terms of being able to detect a shift. In fact, my simulation used the same rules or alarms, warnings, Nelson's 1, 2, 5, and 6. We can see that with the second class gauge, we're going to attenuate process signal a little bit. So we're going to attenuate some of the true part signal a little bit through the gauge. But our probability of warning on a single alarm, just one.
Just test one, okay.
Just one, it's still somewhere between, close to 90%, close to 100%. If we're looking at more than one alarm, in fact, if we're looking at all 4, then we can expect very near 100% probability that we're going to pick up a shift in the process, 3 sigma. And we can run that simulation for even smaller shifts in the process if it's necessary. So now think about it, Clark. What are your thoughts? This is your gauge, and you're in the second class zone. You're very likely, what are you going to do next is probably the best question.
I'm going to come back to this risk concept too and say, well, I'm making chef knives and not airbags. So I really start to question myself, like second class monitor, again, using this monitor strategy seems to be adequate for me. And maybe I'd investigate that interaction a little bit. Maybe if we just implement a simple fixture. But this is telling me I might not do much about that. I think I'm okay. Let's bring these shun knives up to production.
I like it. Yeah, that definitely, I love that thought process, because we're really thinking about how we're using the gauge. We're not condemning the gauge. yeah, sure, it's a second class gauge, but we just had the conversation and decided that that was perfectly adequate.
Right.
So we're already moving into a world that's a lot more comfortable for me than the methods that you and I grew up on, the percent R&R. Should we do the final one real quick? We've got probable error. What's EMP telling us we need to do?
Oh, it's got the recommendation right there on the significant digits. Drop a digit.
Drop a digit. Yeah, so it's based on probable error. Our current measurement increment is smaller than our lower bound and smallest effective increment. So we would want to round the measurement up. We don't have enough time to do that. The way we would go about it is just, create a formula with a round function, round it up until EMP doesn't tell you to drop a digit anymore.
Okay.
So that's awesome. No more arguments about, hey, my gauge is super precise, or the vendor told me this. Well, run the study and let the study tell you what you need.
No more rat holes.
All right. All right, Clark, I think we've come a full lap through MSA.
And the EMP and
EMP.
Jason, thanks for debriefing me on this method. Again, what stands out is the same first law of analytics: visualize, graph your data. And just by the time you create those EMP charts, the average, the standard deviation or range or parallelism, you already get to see what your data looks like. You're already understanding without computing, other computations. So I love that. You already can generate questions out of the gate. And then maybe some other highlights in my brain is averages chart really telling you about the overall utility of that measurement system. And then the range is giving you a quick clue on that test, retest, or repeatability. So I'm sold. Dr. Wheeler, EMP for the win.